Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome to lecture 37, Organic Chemistry 2. Today we will continue on carboxylic acid derivatives and we will cover their reactions. As we mentioned before, the reaction of alpha hydrogen of carboxylic acid with alkoxide will provide the enolate anion. Look at the pK here is 24 and for the alcohol is 15. So the equilibrium will shift to the left hand side of the reaction, mean that the alkoxide will present in good amount that reacts with alkyl halides to form ether. But the target here was reacting the alpha hydrogen to form the enolate anion, then react that with alkyl halide to provide the alkylated species. So this is our target and this is byproduct. To get the target molecule, we need high percent of the enolate anion. So if we start with species alpha hydrogen is between 2 carbonyl, so that will be highly acidic, pKa of 11 compared to alcohol 14. In this case, the equilibrium will shift toward the right hand side and provide high concentration of enolate. Then reacting the enolate with alkyl halide will provide this compound. Still, the ether will be there, but in very low yield. So the first example of the activated methylene group, the malonic ester synthesis, makes substituted derivative of acetic acid. Malonic ester, or what we call diethyl malonate, is alkylated or acylated on the more acidic carbon that is between both carbonyl groups, and the resulting derivatives is hydrolyzed and allowed to decarboxylate. So starting with diethyl malonate, treat that with sodium ethoxide deprotonate to form the enolate with 3 resonance structures. Alkylate with alkyl halide, form this species, then hydrolyze either base hydrolysis or acid hydrolysis. Here we use saponification, base hydrolysis, to form the salt, then neutralize or acidify the salt with acid, you get the free acid, heat up, you decarboxylate minus CO2 and you get your target molecule. So to synthesize such a compound, we can start with Synson R plus and CH2 minus COH. The Synson for the R plus synthetic equivalent is alkyl halide. Synson for the CH2COH, okay, the synthetic equivalent will be the diethyl malonate. Well, to get the complete view of the retro analysis, we are saying now we would like to get the R CH2COOH. So we add here to the alpha carbon COOH. We have dicarboxylic acid. Now we transfer that to an ester, and then we cut in here to get the synthetic equivalence of the R plus alkyl halide and the diethyl malonate for the CH2COH. Any carboxylic acid with beta-Dicarbonyl in the position is prone to decarboxylate. At the temperature of the hydrolysis, the alkyl malonic acid loses CO2 to give substituted derivative of acetic acid. Decarboxylation takes place through cyclic transition state. So here is a carbonyl, gets this H plus, 2 electrons to form a double bond, 2 electrons here to form a double bond, will give the enol form, and CO2, the enol form will tautomerize to the carboxylic acid. Function. Let's practice. Outline a malonic ester synthesis of the following carboxylic acid: 2-methylbentanoic acid. Well, this is the carboxylic acid, here is the alpha carbon, so we add COH. The dicarboxylic acid comes from diester. This is the alpha carbon, we have double alkylation, one with methyl and one with propyl group. So if we cut in here, so it will be methyl bromide with these species, and we get this one from the malonic ester with the propyl bromide. So starting with diethyl malonate, add sodium ethoxide in ethanol and then add the propyl bromide, we get this compound. Sodium ethoxide again to this alpha hydrogen, form the enolate, then react that with methyl bromide, we get this compound. Or what you have to do, saponification with sodium hydroxide water to form the salt, hydrolyze to get the carboxylic acid, heat the carboxylic acid, lose CO2, and get the product. Give the product of the following reaction sequence. Starting with diethyl malonate, add 2 equivalent or excess sodium ethoxide in ethanol, then react this with 1,3-dibromopropan. What do you get? Saponificate that with sodium hydroxide water. What do you get? Then add dilute HCl and heat. You get a compound C5H8O2. So what are these structures? Well, if we do the first step, 2 equivalent sodium ethoxide ethanol, then we add the dibromopropan, we get this compound. So the anion will attack on this carbon first, and then second anion will attack on this carbon to form the cyclobutyl group on the alpha carbon. Then saponification will lead to the formation of the salt. Add HCl will form the carboxylic acid, and while heating you lose CO2 to get the cyclobutane carboxylic acid. So this is the structure of step 1 here, and this is the structure of step 2, and this is the structure final product of step 3, C5H8O2. Acetoacetic ester synthesis. This is the structure of the ethyl acetoacetate. Well, here is the alpha carbon, or we can say the alpha hydrogen. If we add sodium ethoxide, then we get the enolate, again resonance structures. React that with alkyl halide will alkylate this carbon. Saponification will hydrolyze this ester to form a carboxylic acid, of course after neutralization or acidification with HCl. Here we have beta-Carbonyl carboxylic acid. Upon heating you lose CO2 and form R, CH2, C double bond O, CH3. Once again, the Senson R plus, and here is the enolate CH2 minus C double bond O, CH3. The synthetic equivalent for this species will be our ethyl acetoacetate. So, if we look for the retrosynthesis, we replace this hydrogen with CO2 Okay, this is carboxylic acid and comes from the ester, and this species comes from the alkylation of ethyl acetoacetate. Again, the decarboxylation of the beta-carbonyl carboxylic acid, double bond will attack on the hydrogen, 2 electrons will form a double bond. Here we break this carbon bond, the 2 electrons will form a double bond, so we have the enol and the loss of CO2. Tautomerization of the enol will give you the ketone. So this is the structure of our target molecule. Show how the acetoacetic ester synthesis is used to make 3-propyl hex 5-ene 2-on. This is the structure. We would like to get this from the acetoacetic ester, ethyl acetoacetate. Well, we have here alpha carbon to the C double bond OCH3. This carbon has H. Replace the H with COOH, which comes from the ester. Now, what we do is cut on this one of the R group, so we alkylate this using allyl bromide, and this comes from the ethyl acetoacetate with bromopropane. This is a complete retrosynthetic vision. Here the synthesis starting with acetoacetic ester, treat with sodium ethoxide to form the enolate, treat that with propyl bromide or bromopropane. We alkylate the alpha position. We still have one hydrogen on here, acidic hydrogen, so treat this compound with sodium ethoxide, form again the anion, the enolate, treat that with allyl bromide to form this compound. Now we hydrolyze that with acid directly, acid hydrolysis. We hydrolyze this to carboxylic acid. Upon heat, you lose CO2 to form the target molecule. Outline a preparation of 2-methyl-3-pentanone by a reaction sequence that involves at least one Claisen condensation. This is our target molecule, 2-methyl-3-pentanone. Here is the carbonyl. We get to the alpha of it, and we say, okay, alpha, replace this hydrogen with ester, then cut alkyl on the alpha carbon. Here is one methyl, and there are two methyl group actually. So we cut in here, we get to this one to form this species. If we cut in here, we get two molecule of ethyl propionate, which will condense together under the Claisen condensation to form this compound. Well, starting with ethyl propionate, sodium ethoxide ethanol, you get the Claisen product. You treat that with ethoxide, you get the enolate, which you alkylate with methyl bromide to form this species. Then acid hydrolysis of the ester to carboxylic acid. Upon heating, you lose CO2, and you get the target molecule 2-methyl-3-pentanol. Predict the outcome of the following reaction by identifying A, then B, then the final product. Diethyl malonate with sodium ethoxide ethanol. What is the structure? A, reacting A with this dimethyl 1,1-dimethyl oxyrane. In alcohol, we get compound B, C9H14O4. Well, having the diethyl malonate with ethoxide, you form the enolate. The enolate will react with the oxyrene ring opening, with getting to the less substituted carbon, less crowded, attack ring opening to form this compound, this anion. This O will be nucleophile, attacking on the ester functionality to ring closure and forming lactone, C9H14O4. That's compound B, our final product. Okay, remember we have taken what we call it trans-esterification. This is what kind of trans-esterification, but the ester in this case here, the final product is lactone. See you next lecture.